Now, I'll start with the question. What is the goal of the linear algebra? The goal of the linear algebra. The goal of the linear algebra. The goal of linear algebra. The goal is to solve the system of equations. Goal is to solve the system of equations Ax equal to b. But in linear algebra we talk many things. We talk about vector spaces. We talk about the what do you call, right? The bases, independence, dimensions of the vector spaces, diagonalization of the matrix, eigenvectors of the matrix. We do talk about many things of linear algebra. Sometimes those who teach linear algebra, they miss the connection between the topics that we cover to the Ax equal to b. So our aim is to solve the linear set of equations. Where do you get this? The question is, where do you get this? How do you get this? Where do you find these things? Of course, these system of equations depends upon the application. Suppose, for example, if you want to filter the signal, okay, if you want to remove the noise in the signal coming to you, coming to the communication system, right? You want to design, say you want to design the filter. Basically, design of the filter means that getting the filter coefficients, right? So what is the input to this? The input to this is the noisy signal. Noisy signal. What you wanted to get at the output is the desired signal. Desired signal. You can form a matrix, a system of equations, something like this. Let's say the desired signal is let's say b. You may want to solve the system of equations something like this, where b is a desired signal and w is the filter parameters, and the a is the data matrix. A is data matrix, right? So W is the coefficient matrix, coefficient vector, and B is the desired signal. So you may want to, you may have to find, right? To find the filter coefficients, you may have to solve the system of equations system of equations Ax equal to b or AW equal to b. There are the system of equations that you get depends upon the application. Maybe in communication engineering you may find a particular system of equations. In medical imaging you may find a kind of system of equations, and you may find different set of equations in other applications. Now how do we, first what we do is that we try to connect. You already studied the vector spaces. Okay. to solve this, we use the vectors, the linear algebra concepts, right? So let us, before that, we just connect what is the relation between the vector spaces and the system of equations. How do you generate the vector spaces with respect to this, with respect to the A, right? What is the connection between the vector spaces to the Ax equivalent to B? So you may see the column space of A. There are 4 vector spaces that are connected to the A. One is the column space of A, and the other one is null space of A, and row space of A, and null space of A transpose. There are 4 spaces that are connected to the matrix. There are 4 vector spaces that are connected to the A matrix. What is the connection? What is the connection between these spaces and the system of equations? What is the column space here? The column space. The column space. What is the column space? The column space is this. The column space of A is Ax. The column space of A is Ax. What do you mean by this? What do you mean by column space of A? Say for example, a trivial case, let's say the matrix is this. What do you mean by, let's say X is a 2-dimensional vector. What do you mean by this into this? What is Ax? What is the column space? The column space is nothing but the linear combinations of A. The column space is nothing but the linear combination of the vectors. Now you tell me, what is the column space for this matrix? 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 If I take the linear combination of this vector, what is that you are going to see? What kind of vectors that you see? What is that you are going to fill up? Suppose if my x equal to where x takes the value from the real line and y takes the value from the real line. I mean, just I'm diluting to the notations and all, but you just consider the x and y are the values from the real line. Any value. Okay. It can be, if x equal to 0 and y equal to 0, what is the vector? What is the vector? 0, 0. 0, 0 vector is in the column space of A. 0 vector is in the column space of A. 0 vector is in the column space of A. Say x equal to 1 and y equal to 0. And this vector also is in the column space of A. X equal to 0 and y equal to 1. This also is in the column space. X equal to 0.5, y equal to 0.5. What is that vector? The 0.5, 0.5. 0.5 also is in the column space of A. Now, you tell me, what is the column space of A here? The column space of A is the entire R2. Entire R2. Now you are equating the column space. Now what you wanted to have is, we wanted to equate this column space to the B. Ax equal to B. Now if you want to have a solution, if you want to equate this to this, the B should be coming from what? B should be coming from what? You want to equate, so this is not there, this is not there. Now you want to equate this to B. You want to equate this to B. Now B should come from, if you want to equate that, there is a bunch of vectors here, bunch of vectors in the column space of A, right? So that is given by Ax. Now you are bringing another vector which must be equivalent to Ax. Where the B should come from? The B should come from column space of A. So the first thing is, the solution exists. The solution exists if B belongs to the column space. If B is coming from the column space of A, then you will have the solution. If B is not coming from the column space of A, then you will not have the solution. Now for this matrix, if my A is this, let's say my A is this, if my A is this, you would see that for any B you will have the solution. The reason is, the B that you are going to put here is from the column space of A. Any B you take, it may be 1, 2 or 3, 4 or anything that you bring in, B is coming from the column space of A. If B is coming from the column space of A, then there is a solution. So the first condition is, on the right, if you want to have the solution, the B must be coming from the column space of A. Right? So the B must be, suppose you have the matrix something like this. How many of you say that this system of equations have solution? What is the reason that you don't have solution? What is the reason that you don't have solution here? What is the reason that you don't have solution? What is the reason that you don't have solution? 1, 2, 0. Do you have a solution for that? What is the column space of that? What is the column space of that? Can you tell me what is the column space of that? What is the column space of that? What is the column space? The column space is the linear combination of the vectors, column vectors, right? You take the linear combination and check what is the column space. This is the, this is the column space. What is that column space? What is that column space? In the R2, what is the column space? It's not the R square, it is something else. What is that? If I take the linear combination of this, what kind of, suppose like x equal to 0, or x equal to 1, y equal to 0, what is that you get? 1, 0. Okay. Say x equal to 1 and y equal to 1, what is that you get? X equal to 1 and y equal to 1, what is that you get? You get 3, 0, right? whatever may be the, right, whatever may be the, the values, the x and y values, what is the y component here? What is the y component? The y component is 0. The y component is always 0. Only you have the x component. Now you tell me what are the vectors this is going to fill up. This is what? Where the vectors you find? X-axis. Now your vector space is x-axis. The column space is, a line, x-axis. Your column space is x-axis. Your column space is a x-axis. Right? Now look at the B. B is, what is the B here? The B is this, right? Maybe little this one, okay, right? So this is 2, 1. Your B is this. Your B is this. B is coming from the column space of A. B is from this x-axis. No. B is from somewhere else. B is not from the x-axis. Suppose, if I change this vector, if I change this B vector, if I change the B vector as 3, 0, do you have a solution? You have a solution for this? Yes. What is the reason here? What is the reason that you have solution? The B is coming from the x-axis. B is coming from the column space of A. So the first condition, right, to have a solution is the B must be coming from the, B must come from the column space of A. For a particular B, if you have the solution, then that is called the particular solution. You heard about the particular solution? Particular solution and homogeneous solution. Say for particular B, right, you have solution. If B is coming from the column space of A, you will have the solution. That is called the particular solution. That is not the only solution. There is another solution that would exist. There are, like, when other solutions exist is, if there is a null space of A. If there is a null space of A. What do you mean by null space of A? What is that? What do you find? Null space consists of bunch of vectors. Null space consists of a bunch of vectors. Right? So you find the vectors. What are these vectors? These vectors are solution to the Ax equal to 0. Say Xn. So these are the Xn. Let's say the solution that you get for the particular B is Xp. Okay? Now I combine these two solutions. Will it be a solution to the Ax equal to B? Will it be a solution to the Ax equal to B? Will this be a solution to Ax equal to B? Try out, right? So what should we get? When I say this is the solution, right? When I multiply that solution with the A, I should get B. Right? I multiply A, right? What should I get? I should get, what is the Axp? B. And this is, what is this? Xn is a vector which is a solution to this, right? Xn is a solution to this, X equal to 0. If, right, what is that, A into Xn, if this is solution to the X equal to 0, right? So this is 0, so this is equal to B. In addition to XP, particular solution, there are many other solutions. So XP is not only the solution, right? There are, right, because of this, you would see the system of equations will have infinite solutions. If this is not there, only you will have if the solution exists, if the B is coming from the column space of A, you will have only one solution, unique solution. So what are the possible solutions we have here for the system of equations? Unique solution and no solution and one more? Huh? If multiple solution exists, there are infinite solutions. Okay, right? These are the three possible solutions we have. When do you have the unique solution? You will have the unique solution. The condition to have a solution is the condition, right? The condition to have a solution is, right? The first condition is B should come from the column space of A. When you say a system has a solution, B must be coming from the column space of A. Then you can tell about whether this has a unique solution or infinite solution by looking at the null space. If you have a null space, then you will have the if, right? Let's say n of A. If n of A exists, then infinite solutions. If B is not from the column space of A, then no solution. This is the first condition to have no solution. If the B is coming from the column space of A, then you need to check the second condition to say that whether system of equations having a unique solution or infinite solutions. If there exists a null space of A, then you will have the infinite solutions. So for example, let us have, trivial. See, when you don't understand, anything, you just take the trivial example. You will understand everything. Okay. Just take. How many say that? How many solutions this system of equations has? Unique or no solution or infinite solutions? Unique solution. The reason is that the B is from the column space of A. The particular solution exists, right? And if you want to if you want to check this, right, so you need to check whether this system of equations having infinite solutions or not. When do you say this system of equations have infinite solution? How do you check that? You need to check that this system of equations have a solution or not. Can we have a solution for that? Can we have a solution? Can we have, say, solution for this system of equations? No, right? Other than 0, 0 vector, you don't have any other solution. Other than 0 vector, you don't have other solutions. So no, null space vectors. No, right? No vector other than 0 vector would give you, the 0 vector here. There's no null space here. So the system of equations have a unique solutions. Unique solution. Now can you give me the example where the system of equations have infinite solutions? Okay, right? So I'll give you right example. The same example you take. Okay. Now, what is the particular solution here? What is the particular solution? You can straight away tell, right? What is the particular solution here? X into this, y into this. If x equal to 0, y equal to 1, then how do you write this? This you can write it as x into 1 0 plus y into 2 0. Right? If you want to get the b, this other side, your x must be 0 and y must be 1. Right? So this is my solution. This is my solution. X is 0 and y equal to 1. Is that fine? Is that a solution? Right? That is a solution, right? For this b, see one of the vector in the column space is 2 0. See the 2 0 is appearing here itself in the columns. So you can say that you leave this, right? How do you see what is this a into x? A into x is basically x into this plus, right, y into this. You can write like that. You can write this is the linear combination of the vectors. Now this must be equal to 2 0. When this will be equal to, this linear combination is equal to 2 0. If x equal to 0 and y equal to 1, you have the, right? You have the solution. You have, right? If this x equal to 0 and y equal to 1, this entire thing is equal to this. You have the solution, particular solution you have. The particular solution you have. What is xp? xp is 0 1. Can you find the null space solutions for this? What is the null space solution to this? What is the null space solution to this? 0 0, right? So here, what is that? How do you get it? Can you give me any null space solution? Any vector which gives you 0 0 other side. What is that? Sir? Correct, right? So you can write this, right? So you say x equal to, say x equal to 2, x equal to minus 2, y equal to 1. That's the solution. to the Ax equal to 0. Is the only solution? Is the only null space solution? What you can do? The scaled version of that. The scaled version of this is also solution, right? The scaled version of this also solution. Now you add this to the particular solution, right? This is xp plus xn, right? What is the xn here is that 0 1 c into minus 2 into 1. You see how many solutions you get, where c is the constant, okay? C is a value from the real line. C is a constant. You can take any value. It doesn't matter what the the value of c here, but c into this is a solution to the. You multiply c here, right? Take here minus 2 1. It doesn't matter the c is here or not. See, always it will be 0 0. Now how many solutions you have? Infinite. This is the example for the infinite solutions. Okay. Okay, right? So you would see there are different types of system of equations, right, in the literature. How do you differentiate that? Based on the rank of the matrix. Suppose, let's say A is m by n matrix, and the rank of the matrix is R, which is equal to m is equal to n. Right? This is one kind of system of equations. One kind of a system of equations. The second one is, right, A is m by n matrix. The rank of A is equivalent to n, and which is less than m. Okay. This is called the full rank matrix. The system of equations, the number of equations, the number of variables in the system equation depends upon the rank of the matrix. The rank of the matrix. Sorry. It depends upon right. Of course, this, right, m by n. But the solutions of the system of equations depends upon the rank of the matrix. The solution of this system of equations depends upon the rank of the matrix. So these are of course you can differentiate, you can divide this system of equations based on the rank of the matrix. Right? So the other possibility is that other system of equations, right, are possible where the rank of the matrix is R, which is equal to m and which is less than n. And the fourth one is the rank of A is R, which is less than m comma m. For the practical applications, often you don't see this scenario. You don't see this. But in communication problems, we assume that we have this situation where the rank of the matrix is n, which is, you can say that this is which is a full rank matrix. So you may find something like this. You may find the is this, and of course, right, you say that 0 also. Okay. Yeah, so you see that, right? So you don't take this. Then if you don't take this, let's say this other side is okay, right? This is one possibility. Right? This is Ax equivalent to B, where A is m by n size, right? Where A is 3 by 2, and the rank of A is what? What is the rank of A? 2. The rank of A is 2. Rank of A is 2. Which is equivalent to the number of columns. Number of columns. This is, if this is the scenario, then this is called the full column rank. Full column rank. This is a particular type of system of equations. These system of equations often you find in communication engineering, communication engineering problems. For example, if you want to design the, if you want to get the the filter coefficients of the linear filter. Okay. So we assume that here in practical it won't be like this, but we assume that the A has the full column rank. We assume that A has a full column rank. This is one scenario that you see. Okay. But you will understand this scenario if I give the example, if I draw the this, right, I can derive the system of equations, right, from the from the problem of designing the Wiener filter, the problem of designing the Wiener filter. We can always right, but we don't have time, so I cannot show you how you can form the system of equations for the given problem. Okay. So there are cases, right? So you may have to solve the system of equations of this form, or you may have to solve the system of equations of this. You may have to solve the system of equation like this. What is the rank of that? Can anybody tell me what is the rank of that? I just flipped that, okay. This matrix I just flipped, okay. So what is the rank of that matrix? 2, right? A is 2, which is equivalent to the number of rows. The number of rows. This is one case. Often this case you find in medical imaging problems. This is called the over-determined system, and this is under-determined system. Usually right, these are all called, right, in the imaging problem, this is called the measurements, and these are called the unknowns, and this is the matrix obtained from the linear operator, right, it depends actually. Depends upon, this A depends upon the linear operator that you use, okay. It depends on the the linear operator that you use, okay, the linear operator. In these two cases, right, this other case, the special case, we'll come to that, okay. So look at these two cases. These system of equations have a particular, a special case of solutions. By looking at the B, what is the solution to this? What is the solution to this? By looking at the B, it doesn't have a solution. By looking at the B is not come from the column space of A, no solution. No solution. Now how many solutions it has? For a particular B, right? B is here B is coming from the column space of A, and also this system of equations have and this system of equations may have a solution, unique solution, or no solution. But this system of equations have an infinite solution because the B always comes from the column space of A, and in addition there is the null space exists. So here infinite solutions. One case is from communication engineering problem, and one case is from the medical imaging problem. You may have the number of measurements. What happens in a medical imaging problem, most of the cases the number of unknowns more than the measurements that you take. So always you have the underdetermined system in the medical imaging problem. So you will have infinite solutions in this case. In communication, most of the time you don't have solution because in communication problem, this is the desired signal, and these are the coefficients, and this is the data matrix. Data matrix. You will not have most of the time you cannot match, right? You cannot match. This is actually, this data matrix is formed by the noisy data. You cannot match this AX equivalent to B. The assumption is that you cannot match this with the B. You cannot match AX with the desired signal. That is the assumption that we make. So here, suppose if you are able to match, if you know that if you are able to match with the B, the desired signal, then you will have the unique solution. Most of the time it doesn't have a solution. No solution. But here, if this is the scenario, always you have infinite solutions. So if you look at the fourth case, yes.
So what causes the other system, the communication system, to be overdetermined? Are you making more measurements?
More measurement. See, basically, yes, noisy. See, these measurements are more than the unknowns. Why you will have the overdetermined? Because the measurements here. So this is the desired signal. The number of samples that you see in the, right? Usually, right? See, this is maybe the problem from the design of the design of the Wiener filter. The parameters that we want to find for the Wiener filter is, the number of parameters that we want to find for the Wiener filter is less than the number of samples that we get, that we receive. That is the reason you would see this is the overdetermined system, right? And this is the underdetermined system, means the number of measurements that you get is always less than the number of unknowns. The assumption, it's not that right, you always have the infinite solution. The assumption is that this is the full row rank matrix. If it is a full row rank matrix, then you have the infinite solution. So there is a special case. You can see that if the matrix is this, suppose, right, you have the something called, right, so you see what is the case? Let's say you have you take all zeros here, and then here you take, okay. Now you look at this system. Now you look at the system. Z, let's say K, right? It won't be, it won't be a sparse matrix. Just I'm giving the example, okay? It will have full of course, you find the values which are redundant to, other values, okay? You see that, most of the, you don't find zeros here. You find other vectors, but the vectors are, highly, you say that the vectors are dependent, okay? So this is the case. What is the rank of this matrix? Can anybody tell me what is the rank of this matrix? The rank of it. It says 3. 2, which is less than, right? What is that? 4, 4. This is a special case, okay? People wanted to get the solution for all these cases. So the first case is, this is a behaved system of equations, where the rank of the matrix is, the number of columns and rows is a well behaved system, okay. We don't have any problem with this. What is the solution in this case? What is the solution in this case? A inverse B. You don't have any problem with the, right, the first case. But the problem we have is for the second case, third case and fourth case. The problem we have for this case and this case. How do you get the solution? So for the first case, I don't want to know, like we require one more class to explain everything, but I just give you overall what is the solution we will have, okay. So in this case, that the system of equations are well behaved. So in this case, there is something called, right, you say that for this case A inverse exists. When I say A inverse exists, it has a left inverse and right inverse. It has a left inverse and right inverse for the well behaved case. For the second case, this case, the left inverse exists, no right inverse, no right inverse. Only left inverse exists. In this case, you have a right inverse And in this, right, you don't have the left inverse. So the left, the left inverse saves this problem. The solution to this is to do with the left inverse here. The solution to this one is to do with the right inverse, not the left inverse. And here, this case, we don't have left inverse or right inverse. Gone case. Okay, we don't have, we can't use left inverse or right. But this, you can use a particular inverse. You know that. Okay, what is that inverse that we can use here to solve the problems? So pseudo inverse. Right? You heard about the pseudo inverse? Is this spelling? Pseudo inverse, is that correct? A dagger. Okay, this is dagger is something, I don't know how to. So a dagger. For this problem, the solution is this. For this problem, the solution is this. For this problem, we combine these two, and the solution is to do with the A transpose and then A transpose A. It is to do with the eigenvalues of those two matrices. The solution to this is a pseudo inverse. It is to do with the, you heard about this SVD, something called SVD, singular value decomposition. Okay, so yeah. Why we call it as the left inverse and why this is called the right inverse? I'll just give you that. I cannot show you how do you how I cannot in this class I cannot do that. Okay, I cannot do that. What is that? I cannot prove that this is a solution to this problem. Okay, but at least I would say that this is a this is, you can see that from this solution there is possibility that you can have the left inverse for the A. By looking at this solution, we can say that there is a right inverse for the A. So let me I'll do it here. Now we know that the least square solution is this, right? Now what I do is that I take this part and multiply this with, this is the part with A. What would I get? A transpose A inverse A transpose A. What is that you get? Of course, we have to make one more assumption. Assumption is that they should be invertible. Of course, for this case, this is invertible. Okay. Now A transpose A inverse A transpose A. What is that? Identity, right? Then what you would say about this factor? Since this is sitting on the right, left side of A, then you would say that this is the left inverse. And look at this solution. Look at this solution. I'll just do it here. What is the solution? The solution is I take this solution, then what I do is that is the solution. Yeah, right. So I just keep this term on the right side of the right side of A. Then what is this? I. So the assumption is that this is invertible. Okay. See, for this case, the A transpose is invertible. Now, since it is sitting on the right side of A, This is called the right inverse. You know, if you want a solution to this, then you combine the left inverse and right inverse. So you have to work with, here you observe that for this solution we work with the A transpose A, and for this solution we work with the A transpose. So if you want to have the solution, you have to work with the two matrices which are A transpose and A transpose A. Okay, so we don't have time. I just, you know. So do you have any questions from this?
The A transpose A or A transpose is simply to convert a non-square matrix to a square. So
yes, correct. Yeah. And assumption is that if this is the scenario, right? If the rank of the matrix is 2, which is equal to the number of columns, then always A transpose A is invertible. That's why, you know, you could able to do the inverse here. You could able to get, you know, the solution like this. This is called the, what is this called? You have seen, you know, anytime this one in SARS, you know, presentations. Have you seen any time this solution? You have seen, right? Least square solution. Is there least square solution? But this system of equations will have infinite solutions. If you have infinite solution, what is the solution that you take? What is the solution you take? See, in this case, no solution, okay, right? You know, you take the, you know, best out of that, best solution which minimize the error, okay? But here, we have so many solutions, infinite solutions we have. But what is the solution that we take? What is the solution that we take? Any guess? I'll do it here. What is the solution that we take? Put the constraints. You have to put the constraints. It will become, you know, another optimization problem. So what is that you take is, out of infinite solutions, you take the solution which is near to that, near to the origin. So how do you formulate that? So you minimize this subjected to Ax equal to B. And the solution to this is this. Solution to this is this. And this solution gives you, you know, the solution out of, you know, infinite solution which is, you know, near to the origin. Okay, so I think, you know, I'll stop here because, you know, I don't want to get into, right? Maybe if you want me to take, you know, one more class, I'll take one more class and I'll talk about the pseudo inverse, right here. But pseudo inverse is to do with the SVD of the A. You heard about the singular value decomposition, right? So when I use, you know, right, when I use the singular, you know, the pseudo inverse will take to, you know, to the solution depends upon the case we have here. So in this case, in the fourth case, what are possible solutions that we can have in the fourth case? In the fourth case, the possibility is that no solution and infinite solutions. These are the two possible solutions for this. When you don't have solution, this pseudo inverse would take to the least square, when you have a solution, infinite solution, the pseudo inverse will take you to this solution. The reason is that the pseudo inverse involves A transpose A and a transpose. The pseudo inverse takes you to the either this solution or this solution, depending upon the the case here, depending upon the rank. If the rank of depending upon the solution that we have here, if the no solution, then the pseudo inverse will take you to the least square. If there are infinite solutions, right, the pseudo inverse would take you to this solution. So,
an observation, but please tell me if I'm wrong. You mentioned that in this case, in communication, we have an overdetermined system, but that's by design. The filter coefficients are fewer in number than the data samples, signal samples. That's understandable. But in the other case, in
imaging and all,
yeah. For example, in algebraic reconstruction, the image size is much larger than the
image. The unknowns actually. X-ray measurements, right? Yes.
There, those considerations come into play that will limit the number of measurements.
Number of measurements. Correct.
Hence, your
System is underdetermined. Yes.
Is that correct?
Correct. Sir. Yes. Yeah. So, do you have any doubts? If you want me. It's fine, right? This is the summary of linear algebra. I mean, I just like in one class, I covered entire linear algebra. See, this would I talk about this class. I talk about in 40 lectures, around 40 lectures. In 40 lectures in one lecture here. So this is the basic knowledge that we need to have, right? So before you take up any of the course. Okay, so. Right. So any doubts from this solution to the system of equations? Sorry, you may not, I don't know how many of you got the information. So you need to have a little basics of that. So you are telling, so you are from? No, that. No. Second year. BTech. You already done, right? Part of this.
Yes, sir, I have.
Okay. So. Yes.